Hello, Chem 20s. Welcome to our first class of online learning. We're going to jump in and we're going to get going with our solutions unit right away here. So if you're not already there, just like we would in our regular class, we would have our booklet open. It's our brand new, it's green if you picked it up from the school. It's also available in our Google Classroom. It is the one that says Chem 20 Solutions, has a picture of my wife and dog, of my two super hip nephews, and a couple other solution-y type cartoons. You'll also want to get your data booklet out. Let's see, where did I put my data booklet? In particular, we're going to be using page 6 of the data booklet and our solubility chart that we find there. So if you don't already have those things, you want to get those out right away because we're going to get started. Alright, so Chapter 5 is all about solutions. The first lesson that we've got here for today is a fairly easy one, I hope. Lots and lots of review in it. It'll start getting a little bit more difficult tomorrow, but that's okay. It's nothing we can't handle. So, going in and starting to check a few things out. Terms that, I'm going to get rid of that. Terms that I'm sure you have heard before. Excellent. Physical properties versus chemical properties. So physical properties are all about the substance all by itself. So things like the color, the melting point, boiling point, density, luster, hardness, conductivity, malleability, and ductility. If you don't remember what any of those words mean, you may want to look them up real quick. Chemical properties, on the other hand, are all about how it reacts. Right? So how reactive it is, what it reacts with, all of those different pieces. So physical, just about it all by itself. Chemical, about how it reacts. Awesome. Now I'm sure you've seen charts like this before, talking about matter, pure substances, elements, all those different pieces. At this point, I would take the video, I'd put it on pause, and I would go through and I'd see, can I use these terms, so these terms up here, and can we remember how they fit into this particular chart? Again, put your video on pause and see in your notes if you can figure out where we go. We'll meet up in a second or two and we'll go from there. Alright, so I've got my answers up here. How did you do? As I look through, and we'll do a bit of review as we go through as well. So matter is anything with mass and volume, so pretty much anything except for energy. Matter can be broken apart into two separate things. We've got pure substances with definite compositions and mixtures that can be separated by physical means, so fairly easy to separate. With pure substances, we've essentially got compounds. Let's see if I can get a bit of a highlighter for this. We've got compounds. Compounds are two or more elements, and then compounds are broken down into two different types. We've got ionic compounds between a cation and an anion. Easy way to recognize those is, do they start with a metal or start with an H4? And then we've got molecular compounds, which are a whole bunch of nonmetals that are together sharing electrons. Other pure substances that we've got is elements. So these are the elements that show up in our periodic table. And then, of course, matter. So that's our pure substances across the top. Matter, if we follow along, can also be talked about in terms of mixtures. So we've got homogeneous or homogeneous mixtures. So air, brass, stainless steel, etc., etc. These are also known as, let's see, solutions, which is the title, solutions, the title of this unit. And then we've also got heterogeneous mixtures, which you probably learned in earlier courses, were also known as mechanical mixtures. Mechanical mixtures. Perfect. So again, that should be a ton of review. Things that you can do for the next couple seconds. Again, go ahead and put the video on pause, but classify the following substances using the terms provided above. So we've got tap water, gold, sweetened tea, gasoline, ocean water, and seasoning salt. All right. So, going through and checking this out, hopefully we came up with similar answers. Tap water with fluorine and the actual water would be a homogeneous mixture. Gold, an element, assuming that we're talking about pure gold and not necessarily talking about like 14 karat or 10 karat gold where it's actually more of a solution or homogeneous mixture. We've got sweetened tea, so the fact that it's sweetened tells us that there's sugar in it. Sugar would mean it would be a homogeneous mixture. Gasoline, this one might have been a little bit harder. We learned in previous units gasoline was mostly octane, and if it was pure octane, then it would actually be a compound. But because it's actually octane and ethanol and a few other additives that are in there, it's a homogeneous mixture or homogeneous mixture. Ocean water, assuming that it's just the water part, not any seaweed or little bugs or anything like that, would be a homogeneous mixture. And then seasoning salt, as opposed to regular salt, seasoning salt has all the little spices and stuff that are built in. So seasoning salt, a heterogeneous mixture. Cool. So again, hopefully a better review for people. Next thing that we want to talk about, again, something that we've talked about as well, is lots and lots and lots of ionic compounds are soluble in water. Pretty much all of them are soluble to some extent in water. That being said, some dissolve a lot better. So we're given a whole list of compounds right here, and we want to use the solubility table in our data booklet. That's page 6 of our data booklet to determine which of the following ionic compounds would dissolve to form an aqueous solution. So all we're going to do is say it dissolves or it doesn't dissolve. And even then, we could just say it dissolves for some of them. So yeah, let's check out our periodic table. If we don't already have that up, now's the time to get that out. Again, this is on page 6, and this top table is the one that we really want to look at. So if you remember how to use this table, we essentially scroll across the top until we find typically our anion, so our negative. Once we've found our negative, we can scroll down and look for where our positive is. If it falls in this first row, it means it's very soluble, and we would put aqueous, because it would dissolve in water. Or if it doesn't, so slightly soluble means it doesn't really dissolve very well in water, we'd leave it as solid. So if we were to put that in water, it would end up as just a solid clump. So let's check out the first one here, NaF. It's a solid to start. We want to figure out whether or not it dissolves, whether or not it becomes a solution. So NaF, let's go back to that table. I scroll across the top. Oh, there's F right there, so I scroll, I find F, and then I scroll down, and it says most things are highly soluble with fluorine, or fluoridine, I guess I should say, except for these particular pieces down here at the bottom, and I do not see sodium as one of those pieces, so that means it must fall under most. So when we go back to our document over here, we know that this one would indeed dissolve. Let's do one more. Let's look at B. So this is silver acetate is what we're looking at for B. So going back to the table, I am going to clean it up a little bit because it's a bit of a mess. I'm going to attempt to clean it up a little bit because it's a bit of a mess. There we go. That's a little bit better. So sodium acetate. So I scroll across the top, or I think it was silver acetate, sorry, not sodium. Scroll across the top, there's my acetate ion right there. I can scroll down. Looks like most things are going to be high solubility with the acetate ion, but I got to keep looking because there's a couple odd ones, and in reality, silver acetate is actually right there, and silver acetate falls under slightly soluble, which means it doesn't actually dissolve very well when we put that in water. So for B, does not dissolve. We can even write that out. Does not dissolve. So at this point, again, put your video on pause, go through the rest of these. So we got C through H to check out, and see if you can figure out, I think there's only, if my memory is correct, I think there's only 2 of them that actually dissolve at this point. So yeah, see if you can figure out which two dissolve when they're placed in water. Again, put your video on pause, try it out. So, as you check it out, it turns out there are only two others that dissolve. There is C, dissolves well in water, so that's our ammonium sulfide, and there is G, dissolves well in water too. So G, the copper 2 chloride, copper 2 chloride, that one's a bit of a tricky one, right? Because when we look at our solubility table, I scroll across, I find chloride, so here's chloride right here. I scroll down, and yeah, it says most things. I keep going. It looks like copper 1. So if I find copper 1 right here, it would not dissolve very well. But we're not really looking at copper 1. We're looking at copper 2. Copper 2 actually falls under most, which means that it's going to be very, very, very soluble. So again, C and G are the ones that actually dissolve out of just about everything there, or the other ones that are left over. So, empirical differences between molecular and ionic compounds is the next piece that we want to go through and talk about. So empirical are things that are really, really easy to see, feel, things like that. So if I were to make a list here, and I would say ionic versus molecular, a little bit messy, but we got it there. Ionic versus molecular. Like, what do we know about ionic compounds? Well, we know that they conduct electricity in solution. That's one thing that we know about those. Do molecular compounds conduct electricity in solution? They don't, right? So don't conduct electricity ever realistically. Electricity. Perfect. Ionic compounds. What else do we know? They are typically fairly hard. They have a crystal structure when we look at them closely. They have, let's see, high melting point / boiling point, so high melting points and boiling points. And then we look at our molecular compounds. Well, they could be solid, liquid, or gas at room temperature, which means typically lower melting point / boiling point than our ionic compounds. A lot of times we see them as being soft, solid, liquid, or gas. They don't conduct electricity. I think that's probably a pretty good start with those, just kind of remembering the two. So, a couple of ideas. Again, that first section's a ton of review, just an absolute ton of review. The next section, hopefully review again as well, but might be getting into some newer pieces or some stuff that's definitely going to be more important for this unit. So, as we go through, and we'll get a highlighter or something to underline with here, so make sure that you've got essentially the same. We're talking about homogeneous mixtures, or in other words, we're talking about solutions, right? Which is, again, the title of the unit, so it makes sense that we're spending so much time. So, first question is, well, what is a solution? It's any substance that's evenly dispersed through another substance, right? So, it could be solid, liquid, gas, doesn't really matter, but evenly dispersed or distributed through another substance. That's what a solution is. When we talk about homogeneous or homogeneous mixtures, know that solutions and homogeneous mixtures are pretty much the same thing. They're not pure substances, but they are evenly dispersed throughout the mixture, and can have the appearance of a pure substance, even though it's not actually a pure substance. Most liquid state and gas state solutions are transparent, so something else to kind of think about them, which means that you can see through them. And then something else is, just because you can see through something doesn't necessarily talk about its color at all. So it could be colored or colorless, but typically transparent, so see-through. Heterogeneous mixtures, on the other hand, are generally opaque or cloudy, contain particles large enough to disperse light waves. And then mixtures, well, it's matter that can be separated into different parts. So for solutions, evaporation and distillation are pretty good ways to get our mixtures separated. Excuse me. So a solution, that homogeneous mixture again, it's composed of at least one solute and solvent, so we should probably know what those terms are. The solute is the substance that is typically being dissolved, whereas the solvent is the thing that is doing the dissolving. For us, that's pretty much going to be aqueous solutions where we see water as the solvent. That being said, there are other solvents that we look at. So when we're using water as our solvent, we'll typically put our state as aqueous. So for example, if I look down below here, I've got NH3 aqueous, that's ammonia gas. So ammonia gas is my solute, and it's dissolved in water as my solvent. And I know that water is my solvent because it's aqueous. Same thing with the next one here, sodium chloride aqueous. Sodium chloride is my solute, whereas the aqueous part tells me that water is my solvent. The next one's a little bit weird here. We see this alk. So that's iodine, and it's dissolved in alcohol as the solvent. You won't see that very much in Chem 20, to be honest, but it is something to know. Like, we're dealing with aqueous solutions. That's not the only type of solution that there is. So types of solutions that we've got, again, we've already mentioned that the solvents could be solids, liquids, or gases. The solutes could be solids, liquids, or gases. I'm not going to go through this in any kind of detail, but you should have a quick read of this. It gives you a better idea of what we've just talked about. So at this point, you might want to put your video on pause and just kind of see if you can make sense out of the types of solutions. Perfect, so I'll let you do that now, and we'll get back into it in a minute or two. Alright, so big point of this again is the type of solution. So this is the actual state of the solution. You can have liquids, you can have solids, you can have gases, you can have solutes, where the solute is a gas in a liquid in a liquid, the solute is a liquid dissolved in a solid. There's so many different ways that you can look at. That's all that chart is really trying to show, and then of course it gives you various examples for it. Last thing that we really want to talk about for this particular lesson is just the idea of energy changes. So whenever we dissolve a solution, it typically happens in three very distinctive steps. So first and foremost, I guess we should know that when we're talking about energy, we're talking about delta H. You'll deal with that an awful lot in Chem 30. So that's the energy changes as we essentially go through. So the first step always requires energy, because essentially what we're doing, so input energy, it requires energy because we're breaking those ionic bonds, or separating those ionic bonds. So the ionic compound that we had before is a whole bunch of positives and a whole bunch of negatives, and they're bound together with ionic bonds. When we dissolve it, we have to bust those bonds apart. That takes energy. And if it's taking energy in from its environment, you probably remember this term, endothermic. Right? So it's actually taking energy in. The second step is in order to accommodate those dispersed solutes, so from the ionic compound, the water molecules themselves have to separate. So H2O molecules have to separate. And we learned last unit that it's actually hydrogen bonds that are holding together. They separate, they make space, and because again we're breaking those hydrogen bonds for all intents and purposes, it is endothermic. It's taking energy in. Finally, the last step, the only exothermic step that we see, is those new bonds are being formed between the solvent and the solute, and those new bonds being formed are actually now going to give off energy, being, again, exothermic. So whenever we talk about any chemical reaction, the overall energy that we're looking at is the energy required to break the bonds in the solute, plus the energy required to break the bonds in the solvent, so between the solvent molecules, minus the total energy released when those bonds, new bonds form. That's going to give us our total energy change. Now it's very difficult to see those individual pieces of energy. Typically what we look at is our overall energy change. You're going to deal a lot more with this in Chem 30. We're only dealing a little bit, just understanding now that, and we'll maybe even make a quick note of this. So draw, get the old pen back. Breaking bonds takes energy, so it's endothermic, whereas forming bonds gives energy or releases energy, so it is exothermic. Guess I might as well not be lazy with that one too. So that's sort of the big thing from this entire page. Like, you can read, you can go through in a ton of detail, but the biggest thing to check out, breaking bonds is always endothermic and forming bonds is always exothermic. And I lied a little bit before. We've got one more thing to go through. Properties of aqueous solutions. So aqueous solutions, the two that we're looking at is we're looking at ionic versus molecular aqueous solutions. And things to know, ionic compounds, when they are soluble, they do conduct electricity and they're called electrolytes, whereas molecular compounds, not so much. So then remember, they separate into individual molecules, and those individual molecules do not conduct electricity. So when we talk about conductivity, conductivity is how much electricity it can actually conduct, so how well it conducts the electricity. And again, if the solute is ionic, it's an electrolyte, and the solution we would say is electrolytic. If the solute is molecular, it's going to be a non-electrolyte, and we would say that the solution is non-electrolytic. So there's lots of real easy ways to kind of go through and do this. If we ever get back to class, we might look at this where we plug a power outlet into a light bulb, and if it can conduct electricity between the positive and the negative side for the light bulb, you'll see the light bulb actually light up. Hopefully we get back to class sooner than later and we can actually look at that. So that is our lesson, our very, very first lesson. It's fairly note heavy. I would recommend, as you're checking this out, go back, rewrite things in your own word, maybe make some cue cards, things like that, to make sure that you're really understanding what's going on. A lot of this stuff, well, it seems redundant, it's things that we've done before in various science classes. It's going to be very important as we move forward. So that's where we will leave it today, or at least for this lesson. So talk to you later, Chem 20s. Have an excellent rest of your day.